Okay, afternoon all. We're just going to skim through very briefly the geometrical optics part of module 2. Now, we would have done this at Form 5 level, but we just read through, go through it. It's really, really simple. I'm just going to go through the parts that apply to CAPE, as in where we start dealing with virtual images. Now, virtual images and stuff like that usually occurs with concave lenses. At CSEC, we looked at convex lenses. Convex lenses are very easy and straightforward, but concave lenses bend the light and create virtual images. Okay, meaning they give us images that are not straight line images from object to image. So we have here, a concave lens is one that diverges the parallel rays so that they appear. You see the word appear? Appear means it's not actually there. All right, hold on, let me just close off WhatsApp. All right, sorry. So they appear to diverge from some focal point, meaning it did not actually start in from said point. Hence why we call these virtual images, because they don't move the way a real image behaves. So that's to go into our diagram here. We have our biconcave lens, right? And when we have light coming through your concave lens, the light is going to diverge. So that's basically how the physics works. That's what we mean by a divergent lens. As they hit the lens, the light rays move outwards and diverges, right? Okay. So reading again, a concave lens is one that diverges the parallel rays so that they appear to diverge from some focal point. Hence, this focus is a virtual focus. This virtual focus here is where the light rays appear to converge from. I know that's poor English language. That's the best way you can describe it, right? Appear to originate from, as in you can trace back your rays to start from a given point. So if you were to do the way or the mechanism by which your light ray moves, let's follow it. It hits the lens, the middle of the lens. It comes out to the focal point, and then it goes this direction out to give you a divergent ray. Now, because this focus here is virtual meaning it's imaginary. Imaginary doesn't mean that we make it up. Imaginary means that it does not exist in a straight line, orientation from one point to the next. So the match changes for our lens maker equation. Remember, our lens maker equation is usually 1 over F is equal to 1 over U plus 1 over V. So there are two ways to write this equation. The first way is this one. Since the focus is virtual, the formula for the concave lens is minus 1 over F is equal to 1 over U plus 1 over V, where if you recall from Form 5 or the last that I saw you all, remember we have our object distance and our image distance. If this is our lens and this is our object and this is where our image forms, this is looking at concave behaviors. All right, your object distance is the distance between your object and the lens, and your image distance is the distance between your lens and your image. All right, so here we're going to put this as minus 1 over F. The negative here indicates that we have a virtual image. So there are two ways to work with concave lenses. One is to assume or to treat the focal length as being virtual, since it is not really existing at that point. Right. If the real is positive convention is used, then F is negative and V is also negative. All right, so what we're gonna have here, we're gonna have minus 1 over F is equal to plus 1 over U plus 1 over V plus 1 over U. Now, there is another way to write this down. If this is our lens, right, and this is our object, and that object is now going to hit the lens, and the light ray is going to diverge outwards. If you recall ray diagrams from Form 5 or Form 4, when our light rays converge is where our image is going to form. But how on earth would we get images forming if our light rays are moving further and further away from each other? You see how this kind of gives us a kind of bit of a conundrum? Because our light rays are moving away. They're never going to meet on our traditional image side. So this is where we do a little bit of transposing, a little bit of extra drawing, where we draw this line back, right? We draw these two lines back and we see where those two lines meet. And where these two lines meet is where we have our traditional image forming. Now, since our image is on the same side, is on the same side as our object, we have to consider our image distance, which is V, to be a negative value, right? So there are two ways you can do this. You can either make F a negative value, or you can make V a negative value, but you can't make them together negative. Either one or the next is going to be negative. Are you okay with that so far, ladies? Who's Renee Edwards? I could always throw them out after. Let's see who this is. Renee Edwards, who are you? We have an Edwards in the class already.
No, Mrs. Me. Sorry, I can't continue.
Who?
Mackenzie.
Oh, okay. All right. I was now going to throw you out to the room. Okay, so let's just go ahead. All right, so let's just continue reading. So as I said, there are two ways this equation can exist as. We can either have it with F being negative or V being negative, but it cannot be negative together. All right, folks, if you're worried about the drawings disappearing, remember I am recording the session, so you can always look back at the recording to see where we have the drawings and whatnot. So moving on, power of a lens. Now power of a lens tells you how strong a lens is, which is kind of common sense. And there's an easy way to determine the power of your lens. Power is defined by 1 over your focal length. Now, if anybody here has glasses, who here has glasses? Okay, nobody here has glasses beside me. All right, if you all ever get lenses prescriptions and look at them, you're going to realize that people end up with a positive 1 or 2 diopter reading, or they can have a negative 1, 2, 3, 4 diopter reading. The positive is going to indicate that that person is, their focal length is positive. And when we have a negative diopter reading, that means your focal length is going to be negative, right? Remember, if you change a fraction, reverse a fraction, your sign remains the same. So here, this is how we use powers. Powers, unit of power is called the diopters, right? Given by a D. So if anybody, I will see if I could find my glasses prescription and I'll show you. Somewhere I have it, all right? But those who watch the recording, those who wear glasses, take a look at your glasses prescription if you've ever gotten it, and you're going to see that they actually do write what is the power of your lens. So it tells you what is the focal length of the lens. All right, and this is usually how we measure or record powers of lenses, particularly you see it in spectacles. You don't really see it anywhere else because it's not something commonplace to use. All right, so for your own sake, just learn that power is equal to 1 over your focal length. And please note your power could be positive or negative. Power positive indicates, this is where you all can write this down if you want. Positive indicates that you have a convex lens, and negative power indicates that you have a concave lens. All right, how cool is that? You can indicate what lens you have just by looking at the sign. All right? So that's really cool that, you know, really simple ways of defining what type of lens you're working with just by looking at the numbers and signs. So moving on, note that the power of a convex, okay. I didn't even read this as yet. So that's what they said. Magnification, you should have done this in CSEC, but it's just to revise. CSEC here, magnification is given by the height of the image divided by the height of the object, or H1 over H0. You know, naught, if anything, is usually your original value, the value that you start off with. Or it's given by V over U. All right, so you have two ways to determine the magnification of an image after it passed through a lens. All right, just a reminder, I do have all sorts of activities or interactions available for you all. It's a paid account. So if you all want anything, want to put your hand up, you want to ask a question, feel free. All right, throw it in the chat too. All right, don't feel shy. Ask as many questions as you can or want to. All right, so I just pulled up the side view, so I will see who has questions. Fiber optic cables and telecommunications. You all can read this up, all right? But just to give you really quick, telecommunications, we use a fiber optic cable as opposed to long ago, we used to use copper, as in, we still use copper, right? Now, copper is the preferred material that we use to send electrical signals in. But the problem with electrical signals, and we're going to see this in Unit 2, is when a, let's put this in copper. I do have copper color. Right? So say you have a copper cable, right? This copper cable can only carry a certain amount of electrical signals at a time, right? Because remember, it's the size of an electron. Well, it's a little bigger than an electron. And electrons can interfere with each other. Electrons are susceptible to resistance and temperature. So old school way of using a copper cable for communication, particularly for communication, is no longer the standard in the industry. What we use now, we use a fiber optic cable, right? Anybody knows what a fiber optic cable is? Ever encountered a fiber optic cable before? The name, here it mentioned anywhere for some reason. Anybody? Yeah? What do you know a fiber optic cable is?
I know it lights up. It has like light to it. I've seen out of I'm not calling to my
That's okay, right? Annabelle Mackenzie, you ever heard of fiber optic cables or know anything about them?
No, ma'am.
No. You can give me thumbs up, thumbs down if you don't know, yes or no, tick or correct if you don't know, if you don't want to speak. All right. So what a fiber optic cable?
But
what?
I don't know what. I thought I heard the word already, but I don't really know what it is.
Now, fiber optic cable is simply something that is made up of fibers. Let me look at the English language. It is basically it's a cable made up of fibers that are able to carry light. Optics mean light. So it's essentially a lot of fine glass fibers, right? Usually made out of fiberglass, so it's not as brittle as regular glass, right? But it's made up of really, really small lines of glass. And what this glass does, it has a refractive index such that when you fire light into it, total internal reflection occurs. Do you all remember what total internal reflection is? Silence indicate no. Please go and read that up. Total internal reflection is where we have, instead of having refraction, we end up having reflection, because this is glass. This light can pass through this glass. This glass is not coated with aluminum paint or silver paint or anything like that to make the light bounce around. This is strictly glass, transparent, colorless glass. All right, but what it is, they fire in the light at the exact angle that will produce total internal reflection, as opposed to the light getting refracted out. So by it producing total internal reflection, obeying the law of reflection, which is your angle of incidence is equal to the angle of reflection. So if it enters at the angle of incidence, it is going to maintain this angle straight through. So your light now is going to bounce around all within the cable itself. Think about how fascinating that is. You have a piece of glass where we could fire light into it, and the light remains in that sheet of glass. And as far as I know, we make glass to see through glass. And here we have a piece of glass that has strictly, all we do is just fire the light in at the right angle, and it keeps the light inside of that glass. Now, why do we use this in communication? The size of a light ray is very, very small. The wavelength of light is about 600 nanometers, or 6 by 10 to the minus 7 meters. Look how small that is. So even if this cable is a millimeter across, think about how many light rays we can fit in that 1 millimeter across cable, right? And we don't always have to fit the only one color of light. Light exists from 500 nanometers to 700 nanometers. So imagine we can take every single fraction of light, every single color of light, every single wavelength of light, and fire it into here, and they one will not interfere with each other, right? Which is another really cool thing. They don't interfere with each other. Heat doesn't affect light. There is no such thing as resistance affecting light. So this is how telecommunications uses fiber optic cables now, because we don't have all of the problems associated with copper cables. And you know what? Nobody's going to go and cut down fiber optic cables because then nobody's selling fiber optic cables. Like how, you know, if you read in the news now, people are cutting down copper cables. They don't do that for fiber optics because no one buys fiber optic cables, because it's essentially a cable full of glass. Who's going to use that? All right, so think about how cool this is. This is really, really, really awesome and fascinating that they came up with this. So if you all ever look at your Christmas trees, right? There are Christmas trees, right, that have fiber optic wires or fiber optic lines in all of the branches. I'm pretty sure you all seen that during Christmas time. If you haven't, go and pay attention this holidays, right? As in at the end of every single branch, you can see all the light shining through at the end of the cable, because what it did, it creates light somewhere at the bottom, and the Christmas tree is full of fiber optic cables. And at the end, you see light from all of them. All right, but other than decorative, we use fiber optics for telecommunication that is not wireless. Right? Wireless communication does have its drawbacks, right? Well, the first big thing to know, one of the drawbacks of wireless communication is the weather. The weather makes a big problem with wireless communications. So this is why we still get internet. We don't get internet from satellites, we get internet through underwater cables. Right, and we had a really funny story, as in we did have a cable outage, meaning an internet outage, because a shark had bitten one of the underground fiber optic cables. Oh, I'm not joking about that one. A shark, right, bit one of the cables, and then we need to go and repair the cable. So we had no internet. Okay, so moving on. So if they ever bring up to speak about why we use fiber optics for communication, I'll be, look it up a little bit and go through it a little bit more and see what not. Okay, so moving on, lenses. Glass can be molded into any shape to make lenses of any shape. The shape of the lens will be determined by the use to which it is to be put. It's like we don't make lenses randomly. We make lenses for specific purposes. Okay. Oh, sorry. Okay, so the two main types of lenses, we have biconvex and we have concave lenses. You're going to read through this and go through them. It's not too hard to look at, right? Converging lenses and diverging lenses, convex lenses, any type of convex lens is a converging lens, and any type of concave lens is a diverging lens. Right. One face of a lens can be considered to be a piece of a glass sphere of radius r. Let's think about this. If I have a big circle, we all know lenses are a nice little piece of curved glass. This is the lens that we use in school, no? About this shape here, right? That is about how much of the lens we use. So usually they make they can consider it to be part of a large circle or a large lens with a cutout piece. And look, because it's a circle, every single part of the circle will have the same dimension because they have the same curve, right? Because that's the nice about a circle, it's even all the way around. So we can consider a lens to be a piece of a very large glass sphere. And we can use this analogy to determine the focal length of a lens. Before we were looking at how lenses work, and to get your focal length, here's where we use a physical characteristic of your lens or of your material to give you your focal length. So we can say here for a thin lens, so this only works for very thin lenses. They're really big, huge, fat lenses. But we're not looking at those. Thin lenses are, which is the radius of your large circle that it came from, meaning, you see here where we're cutting out small lenses from all around. R is the radius of the huge circle that it came from, is equal to 2 by your focal length. We have no need to go into the actual physics behind this. It's just something else to learn. So before we were looking at how object distance and image distance give you a focal length. Here we're going to look at actual manufacturing process that gives us our focal length. The eye. All right, so let's go into with the eye. The eye is the focus. The eye focuses on an image of a distant object on the retina. You all should know the parts of the eye, right, where light starts from and ends up. All right, if you all want me to go through in detail parts of the eye, tell me, but it's not really something that we do at CAPE level. You have to know more than just that. So we know, that's looking at the outside of the eye, we know when light comes into the eye, it hits your cornea, it passes through the lens, and it falls onto your retina, right? And at the retina, those rays are converted into electrical signals, which are then fed to your brain to analyze what you're seeing. So let's read. Most refraction takes place at the ear to cornea boundaries, and this is the highest refractive part of our eye. It is your cornea. Okay. So let's read. How does the eye adjust to form sharp images on the retina for varying object distances? So we know that we can look at something, right? If this is our eye, this is the side view of our eye. Some night flashes, right? We can look at something kind of close pretty close to us. And then we can look at something really, really, really far away. That's my terrible tree. All right, we can look at a tree far, far, far away. And these are going to require us having different focal lengths to view different images. Because remember, the focal length tells you how close you can view something. Our eye is able to focus at different distances. And how does it do that? Right? It does that by changing the size of our lens. Right? So let's just read. This is where we're going to go a little bit more into detail of the actual words that we deal with in sight. So from the formula of 1 over f is equal to 1 over u plus 1 over v, v is a constant, right? Being the size of the eyeball. So let's just think about this. If you are looking at something, so this is, let's say this is the eye, right? As your lens to your fovea, this distance is a constant. The distance between your lens and your fovea, the lens in your retina, is a constant. But we can look at things that are at much greater or closer distances. So your U is going to vary. Right? So if your U varies and your V is constant, that means your focal length is also going to have to change. So let's continue reading. So if U varies, then F must vary. The eye varies the focal length of its lens by becoming fatter or thinner, and this is called accommodation. All right, so the process of changing from close to far, viewing from near to far, is called accommodation. Right? The ciliary muscles and the suspensory ligaments are responsible for this process. Okay. For a given adjustment of the eye, which is accommodation, remember accommodation is the process of us changing our focal length or changing, looking from near to far. Or just changing the distances, as you can look at something, say, an arm's length in front of you, you can look at something across the room, 2 different distances. So that is called accommodation. Your eye has to change its focal length to view properly. So for a given adjustment of the eye, accommodation, the eye is able to see clearly an object slightly nearer and slightly further than some fixed object. This variation in distance, through which the eye can still see clearly for given accommodation, is called depth of focus. So depth of focus is where we can view something clearly, even though we're not looking at it. So what I want you all to do right now is to look at, say, put your hand, arm's length in front of you. Do it right now as I explain. Now, if you put your hand in front of you, you will be able to see the things around it, either very blurry or pretty clearly. Now, you're not looking at the things around your hand, you're looking at your hand. So say you're putting your hand in front of you, in front of the desk or in front of the laptop, right? And you look at your hand, you're going to realize that the laptop is a bit fuzzy behind your hand. You noticing that? Give me a thumbs up. Oh, yes. Look at your hand, right? As in you're looking at your hand in front of your face, as in put it in front of the laptop right now, right? Put your hand there, arm's length, and you realize that your hand looks pretty clear, but everything around your hand, like the screen right now, is going to look a little fuzzy. You're not looking at the screen, you're looking at your hand. You all see it? Right? And if you decide to look at the screen, your hands are now going to turn fuzzy. How are we doing, y'all? Of course, we record. Okay, so this variation in the distance through which the eye can still see clearly for a given accommodation is called your depth of focus. Now, your depth of focus is not large. It's really small, right? Well, for us as humans, it is. So effects of the eye. Excuse me. So we have here one, short-sightedness or myopia. I'm going to glance over this. You all can read this when you finish. Myopia is simply when you cannot view distant objects far enough, right? And when you can't see something that is far away, that means that your lens cannot get thin enough, cannot be stretched thin enough to view something far away clearly. All right, so let's just see what happens. Basically what happens, because the lens cannot get thick enough, that means the lens is still a bit too strong, so it causes the light rays to converge in front of the retina. You need those light rays to converge directly on the retina for you to see a clear image. So because the light rays are coming together too soon, right, what we need to do, we need to force them apart. So what we have to do, instead of they coming together too soon, we have to just make them move away from each other. And how do we do that? We use a concave lens. A concave lens, if you recall, means it's a diverging lens, so it forces the light rays apart, right? Such that the light, when it passes through the lens in your eye, will focus them onto your retina. Because your lens is not strong enough, or the muscles are not strong enough to make this lens thin. So what it does, it causes it to bend in too much normally. So because it's bending in too much normally, if we cause those light rays to spread out more, because it's still pretty powerful, it's going to make the light rays hit the right spot on your retina. All right, so what you just have to remember is for short-sighted people or myopic people, with myopia, use a concave lens to spread the light rays apart so that they will hit the retina at the right point. Note, the person will now have difficulty focusing on a near image with their glasses on. Right, so sometimes people who have very strong lenses that need to see far, it's difficult for them to read close, right? Because that lens is meant to push the light rays as far away as possible. Long-sightedness, hypermetropia. Hypermetropia is when somebody cannot see, when they cannot see near objects clearly, meaning people who require reading glasses. All right, so what we have here, this is because the lens is not able to become powerful enough to converge light rays on your retina. For us to view something close, your retina has to, not your retina, your lens has to get very, very thick, all right? So it has to dilate and get really, really thick so that it's strong enough to force these very close light rays together onto your retina. But what happens with somebody with hypermetropia, that lens does not get thick enough to cause the light rays to hit our retina at the right point. So what do we do in this case? We use a convex lens, right? Because let's just recall, this lens here is not strong enough to make the light rays come together at the right point. So guess what? Let's help it out and bring them a little closer together. So long sight is corrected by using a convex lens in front of the eye. So what it does, it brings the light slightly closer together so that we know the lens could only do so much. So it's going to help bring those light rays close enough together for the lenses in your eye to do the job. All right, astigmatism. This is a kind of rare problem. Not rare, it's a different problem from myopia and hypermetropia. Hypermetropia and myopia usually is associated with the muscles and the lens not being able to work properly. Astigmatism comes from the cornea itself. So let's read. A person suffering from astigmatism has difficulty focusing light in certain planes. This is because the curvature of the cornea is not the same in all planes. It is not unusual to see people with this problem bending sideways to see an object properly. So what happens with astigmatism? Your cornea is supposed to be a nice, smooth curve, right? So that the light bends at given angles to enter your pupil, right? Let's say this is your iris here, and this little spot here is your pupil. Your cornea is made in such a way that all the light refracts towards the pupil in your eye, and after the pupil in your eye is your lens. So that is basically what the cornea does. It bends all the light to the right point. Now, what happens to somebody who has astigmatism? The cornea here is not perfectly smooth. It has little dips or valleys, or they're shaped irregularly. And what happens when something has an irregular shape? That means the refraction is going to be all over the place. So that means not all of the light rays are going to enter the eye properly, right? And if not all the light rays are entering, you're going to see a blurry image, or in this case, because they're looking at something at different angles, you can see things at okay angles. You can see things pretty okay at some angles and not okay at others. A big problem with people who have astigmatism, if they look at like a light in the nighttime, they'll see it twinkling. Anybody here ever looked at like a street light in the nighttime and see that it does this? Gives you a really nice, pretty twinkle. No? Anybody? Let me see, and I'll show you what the difference are. All right, so tell me if you see this with your eyes when you have images. All right, so let me stop share. And let's try this next screen. So this is the difference between somebody who has astigmatism and somebody who sees normal. The image on our right is what people see normally. Suppose, your screen clean and your windscreen nice and clean and no water and too much. You see everything with a little glow around it, right? Especially in nighttime. But somebody with astigmatism, because the light is bouncing off the eye at different angles, we're going to have light bouncing around too. And you get these very, very distracting, you all follow my mouse, my cursor, right? You get these very distracting twinkling of lights happening in nighttime. This could be pretty dangerous in the nighttime because you can't make out, you can't make out where a vehicle actually is. You just see what the lights are. All right, so there's a big difference that you see one with people with astigmatism. They see very poorly in the nighttime, right? And sometimes they have to turn their head to see properly. All right, back to the handout. All right, so astigmatism can be corrected by using a cylindrical lens. So as opposed to, is my mic okay? Yes. So as opposed to before we had somebody using a convex lens or concave lens, astigmatism is corrected by using a cylindrical lens. So a cylindrical lens is basically like this, like a cylinder. So the light rays are refracted in one plane. The lens is mounted in the frame in such a way that the axis of the lens is perpendicular to the axis on which the eyes are cylindrical. So this is a very cool way that I realized they had to look at what the orientation of the cornea is and then line up that lens to match, right? Or to cancel the problem that the cornea has. All right, well, before we go on, now it's not unheard of that people with astigmatism usually can have another eye defect with them too. Some people have astigmatism and myopia. I'll be me. All right? Some people, not many people have hypermetropia and astigmatism, but a lot of people who have astigmatism can also have myopia. Cataract. Cataract is not a optical event. It's what we call a metabolic problem. So let's just read it. Cataract is a cloudiness of the eye, natural lens. The lens of the eye is mostly water and protein, protoplasm. Right? These proteins align themselves precisely to allow light to pass through. With age, these proteins start to clump up and start to cloud the lens to avoid leading to clouded vision. Right? So we have here, right, ways to keep your eyes nice and healthy. So what happens for people who have cataract? Cataract, you usually use very strong lenses, but eventually, essentially, so at some point that cataract has made the entire lens so cloudy that you cannot see through them. What they usually do, we can replace the lens with surgery, right? So we can go and get a similar type of material, synthetic material that is, not biological, but it acts the same way, right? And the person here will get nice, clean images. Now, once somebody gets surgery for cataract and get new lenses in, they will have perfect eyesight for the rest of their life. Now, they are also looking into having eye drops that will dissolve the cataract. They're nearly there, to the point where people won't need a surgery again. Okay, so we're getting there. Biochem is getting there. Optical instruments. Did I miss anything? No, optical instruments. You all read up on cameras. You have to read up on cameras and telescopes, right? They can and will come for exams at some point. They haven't come at all ever before. So you know what? Because they take longer and longer to not show up in exam, the likelihood of them coming to the exam is greater and greater. Sorry. Now CXC did say that they are going to release broad topics in 2 weeks. Folks, that is a trap. That doesn't really help, right? It can tell you what not to study for, but what to exactly study for, no. It's a real trap. But it helped to not study too much. Microscope. All right, so that is it. I think we have one more little part to go through, and I think that's called near sight, near point, and far point. So let me just share. So near point and far point is where you can calculate how far they can see clearly and how far or how strong their lenses can be. All right, so I'm gonna send a little note in that in a while on how to work out near and far point. All right, and then we're gonna do some questions. So tomorrow, if anybody is available tomorrow, all right, so we're gonna have a discussion now. I'll close off the recording now. We'll have a discussion and we'll post it up in the Google Classroom. So end the recording now.